Yeah. Have you? Yeah, you started the recording. Right. Okay. Welcome everybody. Just to start off with some introductions, my name's Simon Smart, and I'm the developer of Disagapp. And then we've also got Tim Lucas with us, who is my supervisor, and he's the maintainer of the disaggregation R package that the app uses. If you have any questions during the workshop, please raise your hand in the chat, and one of us will try and respond to your questions. So an overview of what we're going to go through today. We're going to start with an introduction to what disaggregation regression is. Then we'll do a quick demo of the app using some example data, and then we'll go through all the functionality of the app more slowly, and you can join along using the links I sent to you yesterday. And then after that, you can upload your own data and use that for your own analysis. So disaggregation regression is a method that can be used where you have data that's been aggregated to polygons, where your covariates exist as pixels, and you want to generate a high resolution prediction. And so over here, the example was an example data set of malaria in Madagascar. The model can be used to produce an output like this, showing the rate of the disease. And this is particularly useful for predicting the incidence of diseases that are affected by environmental factors such as temperature and rainfall, etc. And the reason that we developed the Disagapp is because there's quite a high barrier for entry to actually use this method. So you need to know how to use R, the programming language, and then you also need to be able to manipulate all the data that's required to fit the model, which might limit the uptake of the method for potential users in the real world. So I'll hand over to Tim now just to explain some of the theory behind disaggregation regression.
Great, thanks everyone. So one of the fundamental ideas behind the point of this method is the ecological fallacy. So if we start off with these aggregate data, like in the picture Simon showed, so cases aggregated to regions, one thing we could do is aggregate our temperature data or whatever it is as well to those same regions and fit a model to that, and that would be fine. That would be a valid model. But what you can't do is fit a model at that aggregate level and then make a prediction at the high resolution or the pixel level using that same model or that same relationship. This is what the ecological fallacy is. It's the idea that the relationships in the data aren't the same at the aggregate level as at the high resolution level. There's various examples of this, and you can look this up quite easily and see some examples work through. It's due to the sort of how there's heterogeneity in the kind of cases within each region, for example. So beyond that, kind of the state and county boundaries are kind of artificial. They're a line drawn on a map somewhere that may have some reflection in the real world, but certainly not, an absolutely strong reflection in the real world. And things like we'd expect areas either side of a boundary to be quite similar, and perhaps two areas just either side of an administrative boundary may well be more similar to two opposite sides of the same administrative boundary that might be kilometers or hundreds of kilometers away. So it's kind of getting away from that idea that these sort of pretend human state and county boundaries are kind of something real and natural in the real world, and moving towards a way where we can really look at what's going on sort of on the ground at the real level that things are truly occurring. And so again, just to reiterate, the ecological fallacy can occur when we try to extrapolate or try to make predictions from a model fitted at the aggregate level at the pixel level. So this disaggregation regression method avoids that problem completely by explicitly modeling at both levels at the same time. So Simon, if you could move on the slide. So the kind of starting point for understand, I'm not going to go into lots of detail or lots of theory, just to try and give you a couple of kind of touchstones that you can kind of get a sense of what this really is doing. So if we imagine a Poisson regression, which many of you might have seen, very similar to a linear regression even, except we're looking at count data. So here our Y is our counts of disease cases, for example. B0 is an intercept, B1 and X is one covariate, say temperature, and this exponential function is making sure that no matter what's going on in this beta 0, beta 1 bit, our predictions of cases, or our prediction of cases or our predictions of rates is always positive. That's what an exponential does. And you may have also heard this talked about as a log link function. So if you move the exponential onto the other side, it becomes a log, and you've got that. It's all the same thing. So if you hold that in your head for half a second as a sort of a natural thing you might do, and then when Simon goes to the next slide, we'll see what disaggregation regression is doing is very similar. We still have Y is our count data. We've still got beta 0 being an intercept and beta 1 and X being a covariate and a normal kind of regression coefficient. However, now instead of saying there's kind of this one-to-one relationship, we're saying we have many X's, so many measurements of temperature, for example. And so we need to make predictions of the rate of disease or the number of counts of disease in many pixels, and then sum up all those predicted cases. And that's what we kind of compare to our observed case data. So you can see it's very similar. In a lot of ways, it's doing almost exactly the same thing. You can sort of interpret a lot of the model in the same way, except we've got this sum function, which means we've got lots of observations on the right-hand side and only one observation on the left-hand side. Simon, if you can go to the next slide. And so that's shown in this picture. So in this polygon, in this case, we're looking at a whole country. We've just got one observation of how many cases of whatever disease is here in India, 23. But what we want to do is consider the environment at all these different pixels across India, and then add them all together and compare that to what we observe in the real data. So all our environmental covariates and all our random effects are at this high resolution pixel level. We use these to make some pixel level, it says PFPR here, that's a mistake, some pixel level rate, and we combine that with our pixel level population data. Those two combined gives us pixel level cases, and we add them all up. So that's kind of just a schematic which describes, again, this second equation. And then we use kind of statistical methods that is not kind of most people's bread and butter, but this is the idea of the model, and then how we fit that model is all handled by the app, and don't worry about it too much. So if you could go to our next slide, please. So again, this might be familiar to some people and might be very unfamiliar. It depends on your background, but random effects are often important in any statistical analysis, and especially spatial statistical analyses. And the disaggregation package has a couple of these random effects that we use a lot. And so it's just kind of worth explaining quickly what they are and what we're thinking about when we model them. So we've got a continuous spatial random effect. So that's kind of similar to a Krieg term if you're kind of from that kind of geography background where you talk about Krieging. It's the same idea as model-based geostatistics, if you're familiar with that, or it's the same as fitting a spatial GAM. It's just a very flexible sort of component to the model that can model whatever's going on in space. It can kind of fit something to kind of reflect it. We often call this the random field from some, I'm not even sure where that's from, I think it's from physics. But anyway, so we've got this continuous spatial random effect that is important, and we'll see again. We've also got discrete independent random effects. So what this is each observation, each y in that previous equation, has its own random effect, and this is how we model over dispersion. So other methods use negative binomial or quasi-Poisson. Currently, we're using discrete independent random effects. We may add up other options at some point, but that's what that is doing, and that is how over dispersion is handled. We're in a Bayesian setting, so both of these random effects are controlled by hyperparameters. So there is a parameter in the model that says how flexible should the random field be, how flexible should the independent random effects be. Those hyperparameters are learned along with the data because it's a hierarchical Bayesian model. So again, this might be a little bit beyond people and a little bit beyond the scope of this short workshop, but you'll see these kind of hyperparameters with weird names. What have we got? Tau and sigma, I think, rho and sigma, and some others. That's what those parameters are doing. They're controlling how flexible these random effects are. And I think that's me done, Simon. Oh no, I'm introducing this. So we talked a little bit about how we've got our response data related to these polygons, to these regions or counties. So that tells us that the sort of data we might be putting in needs to involve some polygons. And in spatial analysis, these are often handled as .shp files, shape files. So that is what you need for this app. We've got some sort of response data, some counts of how many disease cases there are in each of those polygons. Those counts can either be contained within the shapefile or as a separate table, as a CSV or XLSX. And we've got these higher resolution covariates. It might be temperature rasters, it might be kind of precipitation rasters, for example. So in kind of remote sensing and in a lot of spatial analysis, these are often stored as TIFFs. And so that is what is expected, again, by this app. But as we'll see, a lot of them are downloaded automatically for you. But just say these to kind of reflect back from that schematic, these are the data inputs that the model requires. Some polygons, some sort of response data, either within the polygons or separately, and these covariates on a higher resolution grid, typically which we'd call a raster, and which is stored in a .tiff file. Thank you very much.
Thanks, Tim. So yeah, now I'll just give a quick run through of using the app. So this is just to give you a flavor. We'll go back and explain everything in much more detail later on. So I'm just going to load this example data. So this is for the example data that we showed earlier, the malaria in Madagascar. And once this data set's loaded, we also can automatically load some covariate data just to use in an example. So using this menu here, we can switch through all of the different covariates. So we need to make something called a spatial mesh. First of all, as we prepare the data, this will happen in the background, so I can move on to the next step. And this is dealing with some of the covariates. So if I zoom in here, you can see that these different rasters have slightly different resolutions and origins. And so basically the pixels don't perfectly align. And so we need to deal with that before we can fit the model. So if we click here, then we can see a summary of all of this. And then all we need to do is just pick one of them to use as a template. And now if we go back to here, we can see that they completely align, which you won't be able to see because now they are perfectly aligned. So now I'm just scaling them, which is also necessary to be able to interpret the outputs. And then we just need to select an ID. So now our data is ready to fit the model. And we can just use these default settings for now. Okay, and so now we get this as the output. So this shows the parameters of the model. So we can see nighttime light had a negative effect, but the other covariates will have a positive effect. And this plot shows the model fit for the model, including and excluding the IID effect, which is the sorry, the second of the terms that Tim just discussed in the random effects. And then if we go to predict, we can produce the predictions. So now you can see the predicted rate on the map. And then finally, if we go to this reproduce section and the session code, we can download a document that will contain all of the code that's been used to execute the prediction in the app. And so whatever actions you take in the app can be preserved for the future. This format is just an HTML, but you can also download an RMD, which can be rerun in R to produce the same outputs. Okay. Okay, so now to explain things in more detail, and what I'm going to do is to sort of flip back between the slides and the app as we go through this. So I'm just going to also reset this. The way that the app has been structured is into two things called components, which are the steps in the analysis, and then modules, which are possible options in each of those steps. And so these along the top, the intro, response, covariates, aggregation, prepare, fit, predict, and reproduce are the components. And then inside each of them, there are several different options. And these options are color-coded depending on whether you have to use them or not. So the blue ones are ones which you need to use at least one of. So in the response component, you must use one of the blue ones. The orange ones are ones you have to use. So in the prepare step, there's several that you have to use. And then the pink ones are optional, so they don't need to be used at all. So if we go back to the intro, you can also to go through this introductory tour, which explains various different features of the app. I won't go through each of those, but you can if you wish to. If we try and do something and we haven't, well, there's a problem, then we'll see errors like this. So a little pop-up will appear, and this will also appear in the log window at the top. Then we can also look at there's guidance, so a document written about each of the modules. So this tells us what the module does and also how to use it, and includes some references for that. There's also the component guidance, which tells you about each of the different options for that component. And then you can also save your work as you go along. So at any point during the analysis, you can click Save Session, and you can download a document which you can re-upload again, and the app will be restored. So the load facility is in the intro tab. So if you click on this, you can re-upload that file, and the app will reload to look exactly the same as before. And then, as I showed you just a minute ago, the analysis can be fully replicated by downloading an R Markdown file. So something which is perhaps potentially confusing is the results tab. So I'll just show you this with the example data. So the results tab will show you, yeah, that's not good, will show you what the results for that specific module. So I will just load some data for Madagascar. Okay, so this shows the data that we've just downloaded, but if we click on a different module, that those results won't be shown. So the data that's shown in there depends on the selected module. And yeah, if the module doesn't produce results, then you'll also get a message shown in the results window instead. So it says this particular module doesn't produce results. Okay, so yesterday I sent you all a your own URL to access the app. So these are all slightly different, so that we can all fit the model at once. And we'd like you to navigate in there and load the Madagascar dataset as well. The difference here is that whereas I clicked yes on the option which pops up, I'd like you to then select no. So I'll just show you that here. So so I'm going to select no on this one. So now we just have the response data shown there. So if everyone can do that, and then can proceed to the next step. If everyone could just, I think if I do that, if everyone can just respond to my message there saying hello once you've got the data loaded, that'd be great. And if anyone has lost or hasn't got their URL, please let me know.
I imagine it might be quite difficult on a phone. Is that reasonable, Simon?
It is possible, but yeah, it will be difficult. But you can see how you get on. Is anyone having any problems? Please let us know. Okay, I think we'll probably move on then. So yeah, so once you've got this data loaded, you can look at the look at a histogram of the data in the results tab, and then also a table with all of the data that's contained in it. So if that's sort of if you need to just check the data you've uploaded or anything like that. Okay, so moving on to the covariates. So if we look at the covariate data guidance, we've got various different options for the covariates. We've got accessibility covariates, climate covariates, land use covariates, nighttime lights, distance to water, and population density. And then you can also upload your own covariates as well if you've got them. These are typically downloaded at around 1 kilometre square. And once the data is loaded, they'll be plotted on the map. One thing to note with this is that the downloads occur in the background, so you can move on to the next step before the download's completed. First of all, we've got the accessibility covariates. So these describe how accessible different areas are to either cities or healthcare. And these are provided by the Malaria Atlas project. And there are 3 different options that you can choose from, either the travel time to cities, the motorized travel time to healthcare, or walking only travel time to healthcare. So these just use the whatever data is uploaded to load the data. So you can pick one of these options, click to load data. You'll then see this appears below the logger, telling you that there's something happening in the background. And this will also be spinning. And then on the climate covariates, these are from WorldClim, and that contains 17 different computed variables. So if we go to this module, these were blank. So So for this one, you do need to select the country or countries. So if you've got multiple countries in your data, you could click more than one. We've just got Madagascar. And then this long list has all the different options. So as I said, the most likely ones you want are mean temperature and total precipitation. But you can choose something different if you like. And so then once you've made that selection, you can click load data again. And we see now if we look in the logger, the accessibility data has been downloaded. And if we go to the map, we can see that on there as well. And if we go to the results tab for accessibility, yeah, we can see a histogram and a map of that data as well. So then there's the land use covariates. So this can affect various different things in terms of disease. So the distance to forest or cropland could affect the incidence of vectors. And these are provided by the Copernicus Global Land Service. And this data is available for 2015 to 2019. And then there are various different land uses that are available. So go here and select which one we want to download. So I'm just going to take trees, this one, and select the year and data again. Then there's the nighttime lights. So this is collected by NASA from satellite data. And this is a proxy for economic activity. So where there are nights visible at light, this kind of indicates that there's development. But if you sort of think about that, if there are areas with population but no light, then chances are that's an indication of relative poverty. So these this data is an annual average and is available from 2015 to 2023. And this one also requires the country, but once you've already selected the country, it will be carried over from the previous modules. And so we'll load that as well. And then there's the distance to water covariate. So this is computed from a land use covariate, and this is produced by WorldPop using data from ESA. I'm not going to load that one because I think we've already got enough. But if you wish to, you can. And then there's finally population density. So imagine that some diseases might be either positively or negatively affected by population density. And this data is provided by WorldPop. The data is actually downloaded as a count, and it's then converted to density. And then there are various options here. The data can either be constrained, which is where satellite imagery has been used to locate where buildings are actually present. And that results in data being returned with relatively more zeros. So you get areas that have zero population, and that represents accurately. Or in the unconstrained version, there'll be areas with very low populations instead. So in most situations, you probably want to use the constrained data set. I also won't download that one. Yeah, so yeah, all of my covariates are now loaded. So anybody run into any problems? If you can just say in the chat once you've got some covariates loaded, that'd be great. And yeah, I think as Tim's mentioned, this is the bit I was sort of most concerned about with this workshop, just because we're all trying to download data from the same servers at the same time. But hopefully they will all load, even if it takes a little while. Yeah, so the question in the chat about plotting the nightlight as log values, that's just because the values tend to be very skewed. So these are plotted as log values. That this is just affecting the plotting, so it's not actually affecting the underlying data. It's just to visualize it better. Otherwise, it will basically just appear as a uniform area of low values, basically. So yeah, I'll just mention there is also the ability to upload your own covariates. So it's fairly straightforward. You just click here and select the file, and it will then load the data. Okay, so then we have the aggregation data. This is perhaps, well, at least to myself as a non-statistician, was one of the more confusing parts of this. So the aggregation raster acts as a weighting factor in the model and is analogous to an offset in Poisson regression. And for human epidemiology, this is normally going to be a population count. And the way to think of this is that we'd expect pixels that have higher populations to also have higher instances. And so it's important to include this information in the model. So as I said, in this example, we're just going to want to use the population count. So this is the first option here coming from WorldPop. And this has the same options as I mentioned for the population density covariate, but in most cases you can just keep these as the default values. And as with the night lights, probably just want to plot these as log values just to be able to visualize them better. So that will now start to download. There are some potential cases where you might want to use a different aggregation raster. So there's also an option to use land use data. So for example, if we were looking at a tree disease, then it would be sensible to use the tree land use cover as being analogous to a human population count in the model. And the data for this is from the same source as the land use covariate. Okay, so again, this will probably take a little while for everyone's to load, as we're all getting the data from the same place. So we'll just give it a few minutes if everyone can just say once they've got that. So yeah, the difference between unconstrained and constrained is just the constrained is using satellite data to ensure that the pixels that contain that you only get population recorded where there are is evidence of settlements. So that gives you more zeros in the data basically, and that's helpful when we come to fit the model because all of those pixels can just be discarded. Whereas if it's unconstrained, you'll tend to get areas that have just very low populations rather than zeros. Has anybody not got the aggregation raster loaded? Okay, there's some, so it's obviously some still loading. We can actually move on to the next step though, and that can just carry on in the background. So the next is the prepare data component, and there are several steps that are required to prepare the data. So showed at the beginning with the example. The first thing that we need to do is generate the spatial mesh, and then we need to process the covariates into a consistent format, and then we can also choose to reduce the resolution of the covariates if we wish to. So the spatial mesh basically simplifies the model fitting as we just produce predictions for each of the nodes in the mesh rather than every single pixel. I'll first of all just show the, I'll just use these default settings to show you what the mesh is to start with. This one does take a little while to load, but it's actually, it's not downloading anything. It's just the computation required. Okay. So this is one module where it's really helpful to look at the guidance. So this explains basically what all of the different options for generating this mesh effects. So and the number of nodes in the mesh affects how quick the model will fit, but also the quality of the predictions. So the default value is normally fine for an initial fit, but you may wish to increase that for a final model fit. So for example, by increasing the max edge. So if we change some of these, sorry, no, sorry, I need to decrease this to make it finer. Click mesh, click make mesh again. Sorry. Okay, so now we've got a slightly denser mesh, and we can choose to switch between them with this menu down here. There are also some extra parameters you can choose to set for the boundary, which are also explained in the guidance, but typically you probably don't need to do that. So if everyone's at least started to make the mesh, again, that will happen in the background, and we can move on to the next step. And this is the resampling of the covariates. So at the moment, all the covariates will have slightly different resolutions and also origins. So that's like the alignment of the different pixels. And to be able to fit the model, we need to convert them so that every covariate has a pixel of the same size, and they're all in a vertical stack. So in this module, we can summarize, first of all, the data that we've got at the moment by clicking Prepare Covariate Summary. And this produces a table with all of the covariates and the aggregation raster loaded in. You can choose to also remove the identical rows, so just to highlight what the differences are. And so you can see that, for example, whilst the land use, the tree land use covariate has 1 million pixels, some of the others have got 1.4 million pixels. And then also the origins are slightly different as well. We can just choose really any one of these. It doesn't particularly matter which one we want to use. So, but we just use one of these as a template to then resample all of the other covariates to match that one. So in this case, I'm going to use the tree land use. So I just select that in this menu here and click resample. And now this table okay, well, it should show you that they're all the same now. That's not working for some reason, but that's not terribly important. And then, so I'll just wait till everyone has done that. If you can just say once you've resampled them in the chat, that'd be great. Okay, so then the next step is scaling the covariates. So if we look at the data, for example, precipitation varies from 0 to, or maybe 500 to 4,000, whereas mean temperature has a much lower range. And if we were just to fit the model with the data as it is, it will be hard to interpret the model parameters. And scaling the covariates basically will convert each of these to have a mean of 0 and a standard deviation of 1. And that will allow us to compare their effects more easily. So this one's very simple. We just click scale covariates. And yeah, and then we get the covariates have been scaled in the top. We can then, if we want to, we can switch back to the original values by selecting this menu down here, which seems, so I think I've pressed it too many times, but yeah, you can switch back between the original and the prepared at the bottom there. So we can also check to see whether any covariates are highly correlated. If they are, then we may choose to remove some of them. This module here will produce this one. So this produces a correlation matrix of the covariates, and in this case, none of them are highly correlated, so it doesn't make sense to remove any. But for example, you might find if we'd loaded nighttime lights and urban land use, that those might be quite highly correlated, and there's not much point including both in the model. So we could choose to remove one of those layers down here if we wanted to. So with the data as it is, as I said, the cells are typically around 1 square kilometer. And whilst we can fit the model with the data as it is, it can take a very long time for the model to fit, so at least a few minutes. And we can, and actually there may even be some problems depending on the data that you uploaded. If the data covers a very wide area, then it might actually be too much data to even fit the model on the server. And so we can reduce the resolution for like an initial run and then change it later on. Something seems to have gone wrong on this because it's not working. So apologies for that. I will fix that later on, but I think we should be okay to fit the model with the data as it is. And then, yeah, as I've mentioned, once if this had worked, we can then switch between the original data that we loaded, the high resolution and the low resolution, on using the same menu at the bottom. So yeah, as I've sort of already mentioned this, but the fitting of the models is very RAM intensive, and unfortunately, there's no way to stop the model fitting if there is too much data, and it will basically crashes R in the background and crashes the app. And so the more cells there are, or the more covariates, or the denser the mesh, the more RAM's required. These apps at the moment are running on servers with 16 gigs of RAM each, and that can comfortably fit these models that contain around 1 million cells. But yeah, if you try to do something with too many cells, you will unfortunately lose your progress. So this is where being able to save the data comes in really handy, just as a sort of precaution. Although actually, wait, getting ahead of myself. So we'll just finalize the data preparation first of all. So this step really just brings everything together that we've done so far, puts everything into one single format that's ready to fit the model. All we need to do here is select an ID variable for the polygons, which in this case for Madagascar is ID2. And likewise, in most cases, we want to leave the handle missing data toggle on. So if we just click prepare data, and yeah, then we should see up above data preparation is complete. So yeah, like I said, if you want to at this point, saving is a sensible thing to do. So if we just go to the Save tab and click Save Session, and you'll get a file that's downloading. This will be quite large as it contains all the covariates, but yeah, it should hopefully download fairly quickly. So, I mean, for example, mine's 40 megabytes. So. Jose, just 1 second. I will just load that data. So yeah, Jose, you need to use county names in your case. Has anyone else run into any problems saving? Wise choice. Yeah, I'm fairly confident these should all fit in with these number of cells. So yeah, so I've already done the step. Okay, so then we come to fitting the model in the fit component. So for most epidemiological data, where we've got disease counts for each polygon, the Poisson model is going to be appropriate. But if your response data contained non-integers or negative values, then the Gaussian model should be used. In most cases, so in most cases here we can just use the default values. So the Poisson with a log link function, and we probably want to include the spatial field and the IID effect. So Tim discussed these earlier on. Then you can also, if you wish to, choose to set your own priors for the model, if that makes sense to you. So these values in here are calculated, some of them based on the response data, and so the model will use these ones by default. But if you want to, you can adjust those when you fit the model. So click fit model, and yeah, this step will take a little while.
Should not say
Phew. So now my model has finished fitting as well. Tim, would you like to jump in to explain this one? Because you're probably better at it than I.
Yep. Okay. Hello, everyone. So top right, we've got our regression coefficients, which might be familiar to anyone that's done multiple regression before. It's kind of the same idea, but as we discussed before, this is now within this disaggregation framework. The black points are the kind of central estimate. The blue lines are credible intervals. So in this case, we're in Bayesian framework, so the points are the maximum a posteriori point, the point estimate, and the blue are the credible intervals, 95% credible intervals. On the left-hand side, we've got the intercept, which is nice and easy. That's the same as any intercept in other regression situations. The IID effect log tau parameter, this is how flexible that IID effect is. So if this is a big number, that's saying that the model's allowed to fit large numbers for the IID effect. So the bigger this number is, the more over dispersed and the more kind of missing, the more over dispersed is the best way of saying that. So like directly interpreting the numbers is difficult, but that's kind of what it means. Rho is the spatial range of the continuous random effect. So what this means is, so this is log rho. So you have to exponentiate this to get rho. And rho is the distance needed for the correlation in the random field to be near zero. So this is a 2. I can't remember what exponential of 2 is, but probably 4-ish. So 4 spatial units, defined as whatever the spatial units you've been using in the other parts of your data. Beyond 4 spatial units, that spatial field term will kind of not be spatially correlated. It's a little bit confusing, but that's kind of what it means. Log sigma is how big the variations in that spatial field is. So if sigma is big, we're going to expect, some areas to have very high estimates of this field and some areas to have very low estimates of the field. If it's very low, we're going to expect that field, even if it might be very wiggly, but it's going to be doing very small wiggles. I'm afraid you always end up using words like wiggly with these things, but that's what they are. Do you want me to do the scatter plot as well, Simon?
If you don't mind.
So the scatter plot is just a summary of the model fit in terms of within sample model fit. So the red points are, if we ignore the IID effect, how well does our model fit? Again, within sample, we can see there's certainly some correlation with, with the regions that do have a high rate. We're predicting they have a high rate, but we're perhaps not quite capturing everything that's going on. The blue dots are the how well the model fits if you include this IID effect. But because the IID effect, there's one parameter for every single data point, this nearly always ends up exactly on this 1-1 line. So it's kind of not very useful to see, unless you were doing something sort of clever with your priors or something. But in general, those blue dots will always end up right on this 1-1 line, whereas these orange dots are giving you a sense of how well your model fits within sample.
Thank you. So yeah, we've just got those. Has everybody managed to fit the model? Or anybody run into any problems? Okay. Tim, are you able to respond to that one in the chat?
So, well, I don't exactly know what Disagapp does. In the disaggregation R package, there's an internal number that says whether the model has successfully converged. Simon, in the app, do we check that it's converged and give a warning if it hasn't?
I don't think we do. My feeling is that if it doesn't converge, you would get an error. So if you've got the graphs, I think it has converged, but that may be something we can check up.
Yeah, we'll add that as a to-do to check and confirm and at least give a warning. I'll open an issue for you, Simon.
Great, thanks. Okay, so then if we go to the predict component, there are various options. So by default, the model will be predicting the rate, so cases per person. But we can also choose to include the cases. So that uses the aggregation raster to convert the rate to cases, and we can also include the credible intervals. And then once you've run this, you can download rasters of the predictions. So we typically want to include the ID effect. And in this case, I'll include the cases and include uncertainty. For the uncertainty, there are some more options there, but typically you can just leave those as they are. We'll mention it here. The reason this is taking a long time is because I've included the uncertainty. If you don't include the uncertainty, it will run a lot quicker. Aha. Great. Okay, so now I've got the predictions. So I've got the predictions as rate, predictions as cases, the lower credible interval for the rate and the upper credible interval for the rate. And if I click on that, I can download all the predictions as TIFFs. So we've also got an option here to transfer the model to a new region. If we wanted to, for example, predict based off this model malaria in Zimbabwe, then we could just choose Zimbabwe in here. And if we click this, which I'm not going to here because it takes a long time to run, it will go and download the same covariates for Zimbabwe, and then use the parameters of the model to produce a prediction for Zimbabwe as well. But yeah, as I said, that does take quite a long time to run. So now the analysis is finished. As I mentioned earlier, we can produce a summary. Well, we can download code that reproduces the analysis. So there are various options for this. So there's an R Markdown document which you can rerun in R, or you can produce versions of that either as a PDF, .html, or docx. You can also download a copy of the covariates separately, and when you do that, the R Markdown will be updated to use that file instead of re-downloading the covariates. So this is kind of to secure against the fact that the covariates are coming from web resources, which could potentially stop working in the future. And there's also an option to download a file which enables you to install the exact same versions of the R packages that the app uses, using the R package called renv. So that's in the reproduce environment module. If you click this, it will produce a file which you can then, when you do that, it will then update the R Markdown code to reload all these packages with the exact same versions of currently running in the app to ensure that the analysis is reproducible in the future. So yeah, I've already showed you this for the example data, but I'll show you this again. So I'm just going to download it as an HTML just because it's easier for me to show you now. So each of these little chunks represents one of the modules. So for example, here we're loading the example data and then loading different covariates, etc., building the mesh. So if we could take this code, rerun it in R, and we'd get the same outputs as from the app. So you can also run Disagapp locally on your own computer if you have R installed. It's not currently on CRAN, but we hope to get it onto CRAN shortly. So at the moment, you can install it from GitHub using this code here. And then once the package is installed, you can run Disagapp, and the app will open in your browser. For example, then you could load your saved files. So if, for example, you run into some problems where the model wasn't fitting, then you could transfer this to a more powerful machine to fit the model. Okay, has anybody bought their own data to run their own analysis just before So if no one has, then we can do things slightly differently. But if anybody has bought their own data, can you say? Yes, thank you, Tim, for that typo.
No problem.
I'll fix that, and I'll send the slides around to everyone at the end as well, by the way. Okay, so Tim, are you able to respond to that one?
Yeah, will do.
Okay, sure, thanks. So I skipped over the how you can load your own data running through this. So I'll just go through each of these to start with. So again, remind you, you can read a summary of this in the component guidance. So there are 3 different options depending on what state your data is in at the moment. So if you have a shapefile which contains the response data, you can use the upload shapefile module. If you just have your data in a spreadsheet, so a spreadsheet where you've got one column with the response data and another column with the area name for a polygon, so either the state or the county, you can upload the spreadsheet in this one, and this will then go and download a polygon data and try to merge the 2 together, and will give you any errors, produce errors if there are any problems merging that data. Yeah, so if there are any errors, basically where the polygon in the that's been downloaded and the boundaries that have been downloaded, sorry, and the spreadsheet you've uploaded, then you'll get told which of the names are problematic, and you can then edit your spreadsheet and re-upload it. Then I'll just show you, there's also the option to edit your data. So if I just reload this data. So if once we've got the data loaded in, if for example we only wanted to fit the model to half of this data, we can draw around the area on the map, and then we can either choose to keep the part that's inside or outside this area. So let's keep just the inside bits, and then we can just proceed with this data, with this response data. So I don't think anyone said that they have their own data. So I think we can skip past this bit. So yeah, if anyone has any feedback about this, please let us know. So for example, whether you found it easy to use or whether there's anything that you didn't understand. If you've got data in other formats which you can't upload, and also if there are other covariates that you think could be useful in your analyses, but which aren't available, then we can look at adding those in the future. So my email's there, and also Tim's. And then just a little plug. If you want to make apps that are similar to this, you can use Shiny Scholar, developed alongside this. So it gives you a lot of the sort of framework to produce apps that are reproducible. And then finally, resources. So as I mentioned in the email yesterday, the link that I sent you to use today will only work today. Normally, you should use the address disagapp.le.ac.uk. So that's, again, running on a similar powered server to the links I sent you. But given only one person will probably be using it once, there won't be any problems with multiple models being fitted at the same time, for example. You can view the source code on GitHub, and there's also a document website with documentation on. You can access there too. These slides are also on GitHub, and I will send them around afterwards as well. So lastly, just thank you to Welcome for funding this. And then also thank you to the Wallace developers. So Wallace is an app which we used as the basis to create the app. And so thank you for them to doing quite a lot of the hard work. And then finally, Anita and Andy for developing the disaggregation package. So yeah, that's everything from us. Hope that's been useful. Please let us know if you've got any feedback or any other comments, and we'll try to respond to them.
I'm very happy to stay another half hour if people want to play around and ask questions when they get stuck and anything like that. Use some of the other example data sets.
Yeah, likewise, I'm available if anyone wants to stay.
I realise the New York is a slightly odd example data set because then you have to download the whole of the USA whenever you want to covariate, but oh well. Should I stop recording now? Maybe that's sensible so that
Yeah, that's probably a good idea.
Don't feel quite so whatever. Right, recording ending. Thanks.